Okay, everybody, welcome and thank you so much for having me back again on the Sunshine Coast. It's my pleasure to tell you about the universe and to share the excitement of doing astronomy. So today, I'm going to tell you about stars. I think I was originally tasked with talking about the life and death of stars, but now I've reframed it to talk about the life cycle of stars. And I hope that by the end of the talk, you will understand why I do that. So this is a fabulous picture of the Horsehead Nebula taken from the new Euclid space mission where Canada is a part of. And actually, you can keep an eye out on the news on Wednesday because that is the first data release to the public of the Euclid space mission. And there will be a splash of new images and new science results. Yeah, basically, you'll see a lot more cool images and science being done with the Euclid space mission. But today, I'm not talking about the Euclid space mission. I'm going to talk about something a little bit more philosophical and something we contemplate, and maybe something that you have asked yourself before, or maybe your kids or grandkids have asked. Where did we come from? That is something that I certainly have asked since I was a kid, and I think I was never really satisfied with the answer. And I think there could be many, many answers. And I just want to, well, before I go into science, just to talk about a little bit about how I think it is human experience in common, where even artists like Paul Gauguin here has shown this in his painting, whose title is translated, Where Do We Come From? What Are We? Where Are We Going? And in his painting, he depicts the life cycle of humans, starting from infants to adolescence to adulthood to later ages. And of course, I'm not an artist, so I'm not going to tell you about this painting. If you ask a biologist or people who do research or think about life forms on Earth, maybe what they would tell you to answer the question of where we come from would be that, well, starting from Darwin's theory of evolution, humans came from evolution of other animals, right? And life came from simpler forms of cells. And then over time, there are different varieties of animals, primates, and then that became human, and eventually astronomers looking through the telescope. So that is also not my expertise, and that's not what I'm going to get at today. I'm going to share my perspective from an astronomer, and perhaps you also share that. Where did we come from? When we look at the night sky, I think it's hard not to think about that. And I think there's a lot that we can learn about from looking at stars, as you can imagine. So I want to start by a quote from a French spectroscopist. And in a bit, I will explain what spectroscopy tells us. So I'm going to read out this quote. So the quote goes like, so the whole visible universe is reached by our chemistry and made to furnish the proof that all matter is one, and that these stars are made of the same stuff as we. I think that is something that is profound in the way that actually we are part of the universe. And I will come back to this by the end of the talk, and hopefully I would explain to you why we think that we are made of star stuff, as Carl Sagan put it. So what about spectroscopy? So here is a drawing of Isaac Newton, who is studying the light that comes from a window. So that is sunlight coming through a window. And he had this realization hundreds of years ago that actually what we see as white light is made of stacking lights of different colors, so rainbows. So how did he do this? He did this by putting a prism, which is the device right here, so splitting sunlight into different colors. And this is studies that he published in this book or album called The Optics. So other than having discoveries about the laws of gravitation, he actually also made really profound discoveries related to the studies of light, which of course led to the design of a Newtonian telescope. But I want to mention this because actually it has been centuries of progress where we understand the nature of light, and it is this very understanding that leads us to us to understand that we are actually related to stars. So that was the realization that actually sunlight is more than just white light. It's more interesting than that. So a little bit about spectroscopy too. So of course, well, you would probably recognize this album from Pink Floyd. That is the depiction of a prism. So that is like a medium that could be made of glass or yeah, that disperses light. And in nature, in fact, we already have this phenomena that is explained by the same dispersion of light. So you have rainbows that is related to water droplets in the atmosphere. That is Vancouver. Of course, you recognize that. And there's also astronomical phenomena like sundogs. This is a picture taken from the South Pole, not by me, found it on the internet, but that has to do with ice crystal in the atmosphere that, well, disperses the light. So it shows cool phenomena, right? So what does that have to do with astronomy? So when we're better able to build spectrographs of more precision, this is actually what the sun looks like. Of course, you can look at the sun in different ways, and what astronomers do is to disperse the light. And so this is a stacked picture of the different rainbows. And in addition to the rainbow that you saw previously, you notice something quite remarkable. It is that the presence of these dark bands at particular colors, right? So in fact, in astronomy, so this was an empirical discovery when people discovered the presence of these dark bands. And then in parallel, there's also been discoveries and progress in theoretical physics about the understanding of atomic structure that allows us to relate that actually these dark bands are related to the chemical elements that are present in the sun. So that is where things get really interesting, because in fact, we can do what we call spectroscopy, or taking spectra and analyzing spectra towards the sun and other stars in order to analyze the chemical composition. So by chemical fingerprints, I really mean that we can attribute the individual lines and to calculations from quantum mechanics that allows us to identify which elements are contributing to the absorption of light at this particular wavelengths. So you may or may not be familiar with these symbols, but these are elements that you're already familiar with. So you have hydrogen, iron, magnesium, sodium, oxygen molecule, calcium that you see here, right? So those are things that, or elements that we see in the spectrum of stars, and that allows us to do very interesting calculations to understand, well, then where did these elements come from? So can you put up your hand if you have seen the periodic table or have heard of one? So some of you, most of you, fantastic. So this is an astronomer's version of the periodic table. So what is the periodic table? The periodic table is so at the most fundamental level, matter can be broken down into atoms of different kinds. So the simplest atom would be hydrogen, and then the next one would be helium. So the periodic table is something that you would have learned about in high school if you study chemistry or well, science in general. So in fact, this here is a summary of where the different chemical elements come from. And in fact, I'm not going to talk about it today, but in fact, during the Big Bang, the simplest elements were created. So most of the hydrogen and helium in the universe, a little bit of lithium, came from the Big Bang. And then the rest of the elements, basically everything that we know of comes from stars, or dying stars, to be more specific, the heavier elements. So this is something that is worth thinking about. And just to relate these chemical elements to things that we are familiar with. So the human body is made of primarily water, right? So water would be H2O. So that would be made of hydrogen and oxygen. And the food that we eat, carbohydrates, so rice, noodles, bread, that would be made of primarily carbon and hydrogen. So, and then you take supplements like, I don't know, sodium, magnesium, or whatever, and those are all on the periodic table. Is that a question?
I'm just looking, I've never seen this chart.
Right.
I've seen lots of periodic tables, never seen Dying low mass star and an exploding white dwarf. Are we talking about this, the white dwarf being the final product of the low mass star, or are we talking about different masses? Understand what I'm saying?
Yeah. I think these are like two different processes.
But it would be the same star, for instance.
Yeah, so in terms of mass range, yes.
Okay, so our sun would be one day a dying low mass star, and then it will
Ultimately become a white dwarf,
and
yes.
then it will maybe explode, perhaps.
Yeah, I think white dwarfs, like most white dwarfs, don't explode. But yeah, I think I see what you're getting at, but maybe we can get back to that by the end of the talk. Yeah. Okay, so I think so what you have seen was the chemical spectrum of our sun, and there's actually evidence which came from studies of carbonaceous chondrite meteorites that shows that this is what this plot shows. So what you see here on the vertical axis is the abundance of elements in the sun. And then on the horizontal axis, there's the abundance in this meteorite called Allende. Maybe you have heard of it. Maybe you have a piece of it. That is something you can buy off the shelf. But this is a piece of this Allende or a meteorite like the Allende. So this sort of meteorite are some of the oldest solids that condensate from the formation of the solar system. So you can consider it as pristine tracer of what the solar system was like before it formed into planets. And I find it very remarkable, even though this is something that I teach in the classroom, that for most of the elements, with exceptions, but most of the elements line up one-to-one, right? So that means that we have actual evidence that the solar system and the materials that form the solar system is exactly the same materials that go into the sun, because we form as one thing to begin with. And in a bit, you will see how that is formed. But yeah, that is very interesting to see. So then brings us to the question of how stars are born or were born, right? And this is a brilliant picture of the Orion Nebula, which of course you can see and you may be familiar with. Because that is something you can see through our telescopes. So I have a little movie that I would like to show. So obviously, planets and stars, they form on much, much longer timescales than humans. So that is not something that we can see in lifetime. So astronomers would rely on this sort of simulations in order to try to simulate how this process unfolds. So initially, what we think the paradigm of how stars and planets are formed is that you have an initial cloud of gas, which collapses under its own gravity. So yeah, then yeah, this is okay. This is what it looks like. So it collapses under its own gravity, and this cloud would be initially spinning a little bit, and then as it collapses to smaller and smaller scale, to solar system scale, then it spins more and more. And it is this spin that allows the formation of this protoplanetary disk. And you will see that in the initial phase of the protoplanetary disk, so this would be a protostar. And once a star forms and fusion happens, that's also when a star is born. So before this phase of fusion, which I will talk about in a bit, that is still called a protostar. And in this protostar phase, that is where you can see sometimes jets that are being emanated from the center, because the basically infalling gas would have to get rid of some angular momentum and energy for the system to form and stabilize. And then you can see over multiple orbital times, you start to see gaps in this protoplanetary disk. And these gaps are actually because of protoplanets that are starting to form and coagulate. And then as they orbit in this protoplanetary disk, they sweep out the dust on this plane. So the planets start to grow bigger and bigger. And that is where you can see gaps in this protoplanetary disk. So this is a simulation based on all the evidence we know. But I would say that this formation scenario of stars and planets have been verified because we do have observations of different systems at different stages. For example, when you look at observations of protoplanetary disks, you see that some of them have gaps, and that's when you know that planet starts forming, and then some of them don't have these gaps. So actually people do demographics of planet formation from those observations. So that is pretty much what I want to show you from this movie. Yeah, so this star formation and planet formation, they go hand in hand. And it is this initial spin of the cloud that causes the flattening of the disk. And ultimately, that is also why planets in the solar system, they orbit along the sun in the same orientation, because initially it was one spinning disk spinning in one way, right? So that's why the planets orbit around the stars in the same way. Now, I told you about observations, right? So here is a new James Webb Space Telescope image of two protostars in this system called LINS 483. So what you're seeing here, you don't really see the two stars here because in the initial formation of stars, they are typically very obscured by the presence of interstellar dust. So this the dust will show up as brown patches here, just like when you look at the Milky Way, you can see that towards the galactic center, things are a bit more fuzzy and you don't see a lot of stars. It doesn't mean they're not there. They're just obscured by a lot of dust because it is from this same dust that stars are formed, right? But what you can see here in this protostar system is the strong presence of these jets that you saw in the simulation. And these jets are actually pretty important in throwing out energy from the system so that the stars can form ultimately in the center. So this is quite remarkable. Then I mentioned about the Orion Nebula, and you would have seen it. And yeah, the Orion constellation is one of the most recognizable constellations on the night sky. And so the Orion Nebula is the closest stellar nursery where there's the site of massive star formation, and that is close to the dagger of the Orion. And it is a site where astronomers go back to study again and again, because that is where we can find a lot of massive stars. And if you take a look at the picture, even taken with space telescopes, it's not so easy to see the stars. And what you see is this curtains of gas and dust, right? So here is another simulation that allows us to understand the structure of the Orion Nebula. If you were able to fly through the Orion Nebula in 3D, this is what you will see. So everything is embedded in these curtains of gas and dust, and it is from these kind of sites, deeply embedded within it, that the young stars form. And the reason why the initial phases of star formation is very hard to track is because of this dust obscuring starlight, right? So it helps if we go towards the redder end of the spectrum, like to use the James Webb Space Telescope in order to see better through this dust. But really what is happening here is that when you have young stars that are forming, they emit light, and this light exerts pressure and force to push away the gas and dust around them. This process takes a few million years, so it is easier to see stars that are a bit older, like a few million years after the formation. But the first couple million years is hard because they're always embedded within this phase of dust and gas. So what about our sun? Our sun is not a young star, as you know. It is quite a few billion years old. And of course, actually, we talk about the sun as if it is one thing, one giant fireball, but it's a lot more than that. So what if you were able to cut through the cross-section of the sun? There are a few layers of structure. So there's the core where fusion takes place, where hydrogen is continuously fused into helium. And then outside of the core, you have the so-called radiative zone, where energy is being radiated outwards radially. And then further up in a less dense layer, you have the convective zone, where it is a bit like ocean or atmospheric currents. Things go in circles like that. And then, of course, to the surface of the sun, you have the chromosphere and the corona. And let's see. So as we know, we have seen aurora, right? That has to do with the solar activity. So actually the sun is not just spinning, but actually a very active star in that way that, yeah, you have this different bridges, and there's magnetic fields that is driving these different sunspots and also solar events. And sometimes that sends light and other active particles towards the Earth. So what is happening? What actually defines a star is this process that we call nuclear fusion. And so I know that we talk about nuclear energy, and I know that people who don't study physics can sometimes feel that nuclear energy is dangerous. So I want to explain a bit. Actually, there are different kinds of nuclear energy, and in the sun, the kind of nuclear energy being generated is a different process from what we have as nuclear power plants, which are driven by fission. In the sun, what is happening is that at the core, it is very hot, right? So at the core, it reaches a temperature of 15 million degrees Celsius or Kelvin, as you like. But it is at this very hot phase where nuclear fusion can happen, where you can merge and fuse lighter elements like helium. You put 4 of them together, and that gives you one helium atom. And in this process, which I'm not going to really explain this diagram, when you do this fusion process at the nuclear and atomic level, it releases energy, and that is really what drives, what powers our sun. And I want to talk about nuclear energy also because you may or may not have heard, but on Earth, there are physicists who have been doing experiments with clean energy, clean being not emitting carbon dioxide that heats up our planet. So one of these more experimental nuclear energy would be nuclear fusion. So ITER, or International Thermonuclear Experimental Reactor, is one such expensive experiment that is international, but effectively what the physicists are investigating and trying to demonstrate the feasibility of is that, well, perhaps if there is some way we can create conditions just like on the sun, but on Earth in a reactor, then can't we just harvest the energy and use it to power our energy needs? So again, not really going to go into too much detail here, but what this kind of reactors they have to do is that they have to create conditions on Earth in a lab experiment where they have to create plasma that is 10 times hotter than the sun. So you can imagine the technical challenge, because what kind of material can withstand this high temperature on Earth, right? Millions of degrees Celsius, actually hundreds of millions degrees Celsius. But if this works, then it could be a potential way for us to obtain clean energy, because really we are trying to recreate the sun on Earth here. And if we can just harvest a fraction of that energy, that is already very, very powerful. This works like the sun, that you kind of fuse hydrogen together to form helium, and in this process you try to release the energy. And another technical challenge related to nuclear fusion and its use on Earth is basically, okay, you have this process that causes fusion, and then how do you harvest and store and transmit the energy? So I think these are difficult engineering problems, but I think it's still worth further investigating because of the potential. So that was a bit sidetracked, but so that was about the sun. And I just want to bring up this diagram that you might have heard of, but it is named after 2 astronomers who independently observe different kinds of stars. And they find that actually most stars, they lie on this diagram. So on the vertical axis, that's the luminosity of the sun, so how bright the stars are. And then on the horizontal axis, that would be the temperatures of the stars, or well, a more a quantity that is more directly observable would be really the color and the brightness along this axis. So when you're able to make such observations of different kinds of stars, you find that actually most stars, they lie on one line that we call the main sequence. So the sun is on the main sequence, and then you have other stars everywhere in the Milky Way and outside. They would all lie on this main sequence. And then you have sometimes stars that are in what we call the giant phase, that I will talk a bit more about, or supergiant phase. So those are rare, but when you see those stars, they tend to be bigger and also a lot more luminous for the expected colors. And then down here, you have the so-called white dwarfs, which are the end stage of a star like our sun. So I think there's a lot of interesting physics that go on in here, but the takeaway for this is really that most stars, they lie on the main sequence, and actually we now understand more of the physics of what's going on behind these stars. Is that when stars are on the main sequence, they are in the process of fusing hydrogen into helium, and that is where they spend most of the time on. And that is why when you look at stars of different ages, you find that most of them line up here. And then interesting things happen when stars can no longer do this process because they run out of fuel to fuse into helium. And then, yeah, they could die in different ways, which is what we're going to get into. So you already mentioned that the sun is going to so basically for a star with the sun's mass, it could span about 10 billion years on the main sequence. Now we're about halfway through. So what happens in 5 billion years? Of course, I'm not around to really see this, but what we think happened based on our understanding of stellar evolution is that the star, our sun, is going to become a red giant phase. And as you can guess from the name, a giant star is a lot bigger than the present day. So actually, the sun is going to grow so big that it's going to engulf and vaporize our Earth. And I think at this point, like if I were talking to kids, usually they get a bit scared of that because, yeah, it's a bit difficult to imagine that everything that we know that happens on Earth is going to disappear just like that, right? But it's the way it is. And yeah, I think we're lucky to be here and to contemplate and understand all of this. So what I just showed you is a simulation of the sun when it becomes a red giant, that it would expand so much that it would swallow some of the planets in the inner solar system. The sun at present and the sun at the red giant phase. And actually this red giant phase is a lot compressed. If you look at the scale, like to scale, this would be the comparison yeah, the current size of the sun will be here. And then when the sun becomes a red giant, it's going to be like 100 times larger than the present day, which is why it could vaporize the inner planets. And what happens in the giant phase is that this convective zone that I told you about, kind of on the surface of the sun, is going to be a lot bigger. So it is mostly a giant phase is a phase where materials from the core of the sun could be dredged up and brought to the surface. So that also has interesting implications for how stars enrich the interstellar medium around it. So
sorry, does the core get hotter and that causes it, or does the core get colder and that causes it?
So what happens is that you have fusion that is happening in the center. And then once fusion is done, for example, you have, well, normally on the main sequence, you have hydrogen fusing into helium, right? And then this needs to happen at a hot enough temperature. So when all the hydrogen in the core fuse into helium, then there's no more fusion happening, right? So what happens is that the star would then collapse, or the core of the star collapses under its own gravity. And during this process, so it gets smaller and smaller. And in this process, of gravitational collapse, the core heats up. And when it heats up to hot enough to trigger helium fusion into even heavier elements, then it could fuse into heavier elements, but that would also that is pretty much what is causing this ejection of the outer layers, because it's like the core and the outer gas envelopes, which is now hydrogen and hydrogen rich, because there would be energy being radiated outward from the core that ejected this much less dense layer. So that is what is causing the expansion of the outer layer in the giant phase. Okay. So in fact, it is interesting that you asked this, because normally fusion only happens, as I mentioned, it needs hot enough temperature, but also high enough density to happen, right? So normally fusion happens in the core, but in the giant phase, you can have conditions where you can have fusion happening in the core, but that you can also have hydrogen that is burning in the outer shell. So I think that is, in general, we think of the stars having a structure like onion shells, where you, depending on the temperature of the shells, then different processes could happen. So this giant phase is pretty short-lived compared to the main sequence lifetime. I want to say is about 100 million years or so that it spends on the giant phase. So relatively short compared to the main sequence phase, which is like 10 billion years. And what happens at the end of the sun's lifetime is that you can have an event that is short-lived, that is called planetary nebula. So despite the name, actually the planetary nebula have nothing to do with planets themselves. I think they were so named because when people first discovered that, they thought that they had something to do with planets. But so here are two examples of these planetary nebula who are at end lives of the stellar evolution. So this is the Rain Nebula on the right, and you have the Cat Eye Nebula on the left here. So what happens when fusion no longer happens is that, so actually what makes the sun or other stars a stable structure is that you have an inward force that points towards the core, which is gravity. And then you have another force which points outward, which is gas pressure. So when fusion stops, then there's no longer enough gas pressure. So the star would actually collapse, right? So what happens when there's no more fusion possible, and for this to happen, is that the core will shrink and shrink, and then you would get to a phase where for a star like our sun, then it would end up as what we call a white dwarf, and the planetary nebula is the initial phase of that happening. So when you see the planetary nebula in the center, there's a star that is no longer having fusion. So the star is already dying. And what holds this white dwarf together, actually, I would get to white dwarfs in a bit, but I also want to show you a video of this nebula, and this is in particular for the Ring Nebula, that you see this very nice shell-like structure, and that has to do with the final expansion of material, or what we call ejecta, from the last phase of the star. So actually this structure can be quite complex because it depends on the circumstellar material, because it went through a giant phase, right? So there have been previous envelopes of circumstellar material that had been distributed, and then you can have expansions of different elements. I think that is what is being shown in different colors here. So if you're able to see this structure, again, with spectroscopy, then you can map out the 3D structure of this expansion of the layer, and you can find that actually it's not just radially symmetric structure. There's a lot more to it, depending on which line you're looking at and what kind of elements you're looking at, the expansion is different. Nonetheless, it is beautiful. And yeah, this is like a structure if you were able to see this expansion in 3 dimensions. And of course, this expansion happens on quite long time scales of like tens or even hundreds of thousands of years. So we don't really see this expansion happening in real life, but when you look at different planetary nebula, then you can infer the formation and the age simply based on the geometry of these systems. So I mentioned white dwarf. So what happens after the planetary nebula expands enough, far away enough that the ejecta is gone? What you have left is a so-called white dwarf. So it is a star that is no longer supported by gas pressure, but is supported by what we call electron degeneracy pressure. So I'm not going to explain too much into it, but basically it is a form of what we call compact objects in astrophysics, where you basically try to pack matter as tightly together as possible. And it is the electrons based on quantum mechanics that refuse to get even closer together. So what you're left with is a structure that is called a white dwarf. And so you would know the star Sirius A, but that it actually has a fainter companion that you can see with the Hubble Space Telescope, which is the image shown here, Sirius B, and Sirius B is a white dwarf star. And so just to give a sense of how compact a white dwarf is, that will be eventually what the sun ends up to be. If you were to pack our sun, the mass of our sun, 1 solar mass, into a white dwarf, it would this white dwarf would have a radius of about 6,000 kilometers. So maybe as big as Canada, that's about it. And that is quite remarkable to be able to pack 1 solar mass into, well, basically, yeah, about the size of the Earth. Okay, so far I have given a summary of the life cycle of a sun-like star, starting from the star-forming nebula and the protostars, where you can see jets coming out from them, and then the formation of sun-like star, where it spends most of its time, billions of years, just fusing hydrogen into helium. And then towards the end, you can see it expanding like a red giant, and then ultimately it will go through a planetary nebula stage into a white dwarf. But we know that actually there are different kinds of stars. And in fact, the most fundamental property of a star that determines its fate is its mass, so how heavy it is. And in general, what happens is that more massive stars, they live fast and they die young. So they have a lot more vigorous life, but a lot faster. And I'm going to get to that later, because actually massive stars, so about 8 to 10 times the mass of our sun, they are quite important for the formation of heavier elements that we are familiar with. And then for lower mass stars, so lower mass than our sun, they just live a long time. They spend a lot more time on the main sequence, just fusing hydrogen into helium. And yeah, they don't die a spectacular death. So I'm going to talk about massive stars, and basically they spend less time on the main sequence, but that they go through also a giant or supergiant phase where they just expand to become much, much bigger. But then it is at the end of the life that things get very interesting. It's very fast. They will go through a phase where they explode as a supernova. And depending on how massive they are, they may end up as a neutron star or black hole. And I mean, really, I think these are separate talks, and I'm not going to go into too much detail, but just to give a sense of how a supergiant star, what is the structure, right? Because we talk about a giant star. It is a lot simpler because it doesn't, a star like our sun does not get to fuse heavier elements. But what about a more massive and supergiant star? You have this onion shell structure where you have the lightest elements in shell. So you start from the outermost layer. So this is just the core, right? So you have an outermost layer that is fusing hydrogen into helium, and then inner one inner layer, you have helium fusing into carbon, and then one layer further in, you have carbon fusing into heavier elements, and then you have another layer with a neon fusing, and then you have oxygen fusing, and then you have silicon fusing. So you basically have a stratified core structure of different kinds of fusion happening, and that happens because you have the core does not have one temperature, right? It has a temperature gradient where you have the hottest temperature at the core. That is where you can fuse the heaviest element. And that is why it has this onion shell structure. And then what happens and what goes supernova ultimately is that basically iron is the element which it is like the end of fusion. When you fuse, basically you can no longer make energy by fusing iron atoms together, and that's where fusion stops. And a star can no longer be a star when the core is entirely iron and nickel. So what happens at this point is that when a star can no longer go through further fusion to make energy, there's no longer outward pressure, right? So then the star core would collapse under its own gravity, and it gets so dense that there is this energy which it implodes and explodes into the circumstellar material. And that causes one of the most energetic events in the universe that we call supernova. In fact, it is so energetic that you can see it with your naked eye. So I had not seen this, but has any of you seen the supernova that took off in 1987? So I don't know if it is visible in the Northern Hemisphere, but I just know that it was. So, but if you were in the Southern Hemisphere, I think you would have been able to see it. So the supernova 1987, it happened in the Large Magellanic Cloud, which is in fact 168,000 light years away. So in fact, this supernova did not happen in 1987. It happened hundreds of thousands of years before 1987. And it took light just hundreds of thousands of years to get to us. So this is what the optical image looks like. So before and after, you see that it's like there's a super bright star that appear, right? And that is how remarkable and energetic these events are. And it is interesting to study, and people continue to study this supernova event because basically in the 80s, we already had pretty decent telescopes and we can start monitoring the supernova ejecta. And what you're seeing right here in the middle is actually a time series or sequence of images taken by the Hubble Space Telescope, where you're seeing a rain of circumstellar material lighting up. And what you're seeing is actually the expanding supernova ejecta interacting with circumstellar material. So what was part of the star, and now the supernova expands outwards at almost the speed of light and interacting with this material, right? And it lights it up over the time span of tens of years. And this is a nice and quite recent image taken by the James Webb Space Telescope of the same system. And again, you see this clump and expansion of structure. So I say that supernova are quite remarkable in many different ways, not just because they're bright and energetic, but also because of the remarkable amount of time, right? So we talked about time scale of how fast things happen. So for a solar mass star, for a massive star of 25 times the mass of the sun, actually this core collapse phase that led to a supernova only lasts a quarter of a second, where if you consider the time that this massive star spent on fusing the elements together, it is millions of years, right? I mean, that's still 1,000 times shorter than the main sequence of our sun. So it's only millions of years that it fuses elements together. But then this supernova happens in less than a quarter of a second. So that is where all the energy is packed and then ejected and exploded in a short time. So I want to say that supernova are also incredible because they are so bright that actually you don't even need telescope to have seen it. So that is one famous event that happened in year 1054 that have been documented by astronomers across the world. So that happened, that is a supernova event that happened more than 1000 years ago. And here is the event, and you may have heard or you may be familiar with the Crab Nebula, or the first object in the Messier catalog. And interestingly, actually, because this supernova event was documented so long ago that we are now able to piece it together to understand, well, actually what we are looking at was a supernova that astronomers observed a millennium ago. And actually, what you see here is a very nice space picture taken of this Crab Nebula. And in the middle, what we now know is that there is a pulsar, a kind of a magnetized neutron star compact object in there. And it's death that causes this explosion of event that we know as supernova. And yeah, this is the remnants of its death. And so I say it's interesting because I mean, I'm not a historian, but I know this was bright enough, and it was documented across the world. So I would just highlight two examples. So this is one such event seen in a petroglyph by the ancestral Pueblo peoples that is found in present-day New Mexico. What is being depicted here is that it was thought to be the supernova alongside the crescent moon. Actually, this supernova was bright enough to be seen for more than a year or so. And then what I also found out was that actually there was ancient Chinese astronomers in the Song dynasty who also documented this event as the guest star, because this supernova was so bright that it's brighter than anything else in that constellation. And it is only this century that people are gathering evidence and making translation to understand, well, actually these events were documented across the world, in the Arabic world, in Japanese world, and actually they are related to this Crab Nebula. So to give you a sense of how compact a neutron star would be, I gave you a sense of a white dwarf, that if you packed one solar mass white dwarf, it would be about the size of the Earth. If you packed one solar mass into a neutron star, which is what this pulsar in the Crab Nebula is, this neutron star would only have a radius of 10 kilometers across, so roughly the size of Vancouver proper. And that is how you can make a neutron star. You pack one solar mass of material into the size of Vancouver, and that is how compact and extreme this neutron star is. So there's a lot that can be said about these compact objects, but I think it's a separate talk. And yeah, I'm not going to go into too much details about it. So I just want to come back to this periodic table where, yeah, we talked about how fusion could lead to formation of heavier elements. So again, hydrogen, helium formed from the Big Bang, and then you have fusion that can explain the formation of carbon, nitrogen, oxygen. It really all depends on the mass of the star that is doing this fusion. And roughly, it can explain all the elements of fusion in stars can explain the formation of elements all the way up to about iron. And then past iron, that is where you actually need supernova in order to synthesize these heavier elements like gold, for example. So what happens in supernova is that when the supernova explodes, there is a shock wave in this explosion that could cause extreme conditions that could cause the rapid synthesis of these heavy elements like gold or other heavier elements, which I'm not going to talk too much about. But so all of this happens very, very fast. And yeah, that is why they are called, they're formed in a very rapid way, or they're called rapid process elements. So I want to come back to this life cycle. And I think what I would really like to highlight is that I think of star formation as operating on a cycle. And how is that? So far we talked about for sunlight stars, you form from a nebula, and then you go through a star phase of fusion, and then it dies. And then the same for massive stars, right? But what I did not tell you, and I think is very, very important, is that in all of this explosion of events, That is precisely where the elements synthesized in stars can be then sent back to the so-called interstellar medium. So back to enrich this star-forming nebula with heavier elements. And in fact, this is very important because it is the presence of what we call metals or heavier elements that could make it easier for star formation to happen again in gas stars, in gas and nebula. And the reason of that has a lot to do with how gas can cool, because in order for stars to form within gas, not only they have to undergo gravitational collapse, but they have to have some ways to cool effectively to molecular temperatures of like minus 200 degrees, right? So you actually need the presence of heavier elements in order for this cooling to happen more effectively. So I think of that, that actually when stars form and they die, they enrich the surroundings with more materials that make it easier for the next generation of stars to form. And that is why I say it is a cycle. And this is something that we know happens because we know that the sun did not happen or did not form from pristine material from the Big Bang. It formed from already previously enriched material. And that is why the sun forms, right? So I'm going to sidetrack a little bit, but I think it's important, not just because the Canadian flag is trending these days, but there is actually a mission that Canadians are planning and leading that I would like to tell you about. That is actually also quite relevant to what we can do and learn about stars with this. And this mission is called CASTAR. That is the French word for beavers, which is why the logo has a beaver in it. So CASTAR stands for Cosmological Advanced Survey Telescope for Optical and Ultraviolet Research. So it is a proposed mission, proposed space mission that is a 1 diameter space telescope that is intended to survey the night sky effectively in ultraviolet and visible light with not just imaging, but also spectrographs. So what can CASTAR do? So this is a picture of the Andromeda galaxy, and CASTAR is designed to be a survey telescope, meaning that because Andromeda is so close to us, so basically using the Hubble Space Telescope, you need hundreds of pointings in order to map just one corner of Andromeda. CASTAR is designed to have a wide field of view, and therefore it can survey the entire Andromeda at similar quality with just 6 pointings. So it's an effective survey instrument, and it also has superior imaging quality. So here is a simulated CASTAR image of the ultraviolet night sky compared to GALEX, which was ultraviolet telescope, which was led by NASA. So you can see a lot more detail and structure because it has a better spatial resolution with CASTAR when we get to use it. So CASTAR is going to be useful because, in fact, most of the light from young massive stars, they come out from the ultraviolet. So it is with CASTAR that we can be studying a lot, like millions of stars within the Milky Way, but also millions of white dwarfs by doing these efficient surveys. And we can better understand the stellar evolution cycle by looking at different stages of star formation. So CASTAR is going to be powerful in that way. And right now we are just waiting for the federal government to commit to funding this instrument. But I would just say that this will be the first Canadian-led space mission of this scale. So I think it will be very exciting when it happens. Yes. Okay, then the very last point that I want to make about stars is that, yeah, of course, by learning about stars, we can understand better where we come from. But I think we can also zoom out a lot to think about, well, what about the whole timeline of the universe, right? So far, like we hear a lot about the solar system, our own galaxy. And so the whole timeline of the universe is shown here. There's a lot of physics that go on in here, but we think that it started with the Big Bang. And what I want to show you is that in the earlier phases, so the first hundreds of thousands of years in the universe, we think that, well, there's an epoch that we call the Dark Ages. So it's not because there's no light in the universe, but you can think of the universe, the entire universe, as being an opaque, right? So even if you have light cannot travel freely because it gets absorbed or scattered. So we can't really see through these Dark Ages. What happens is that we think that when the first stars started to form in the universe, they brought about light, and it is this light that turned the universe into being transparent, and so that we can see through it. So this is what we think happened, and that is something that this is things that we can now test with the James Webb Space Telescope. And I just want to say that, actually, we don't quite understand how the first stars formed because, like I told you, we know that most of the stars in the Milky Way, they form from pre-enriched materials that are already full of heavy elements, right? But then the first generations of stars in the universe, they form from these pristine gas made of only hydrogen and helium. So there's not much way for the gas to cool down in order to collapse to form stars. So the first stars must have formed from very, very different conditions from the stars we know of today. But I think they're also very important to understand because we think that they cause a transition in the universe to light up the universe and brought about the end of the Dark Age. So I think that is something that we are actively investigating with the James Webb Space Telescope. So here is one such simulation. I hope, as I mentioned, this is one of the hottest research questions in the universe. So this is something that we need to build the most powerful telescopes like JWST-4. So therefore, most of the studies have been analytic and using simulation. So this is a simulation of the timeline in the earliest phase of the universe history. So you're looking at the first hundreds of millions of years since the Big Bang, and you see an important transition in which initially it's a bit like fireworks. Initially, the universe was opaque, but as the first stars form, then they start to make bubbles around the first stars. And then, these bubbles ultimately connect, and that is what caused the universe to become transparent. So this is an important phase transition that we're actively trying to understand, and there are different theories about it, but I think that's very exciting. Sidetrack a little bit. We talked about the ecosystem in the universe, and I just want to bring it closer to home. When we look at the forest, we see that actually forests are alive when you leave also like the remnants of previous trees, right? You have this older stumps, and then that is actually where you can build younger trees. And then a healthy forest would also have like this dead logs, and that is where it supports ferns and moss, and then also different kinds of birds because they can live on them. And personally, I also think of the universe as being this way, that the previous generations of stars that enrich the gas around it, and that is what makes future star formation easier to happen. So I'm going to leave you with this last quote from Carl Sagan. I'm going to read it out. The cosmos is within us. We are made of star stuff, and we are a way for the universe to know itself. And of course, we know that now we are made of star stuff, but I think what is more profound to me is that we are not just made of star stuff, but we are actually a way of the universe to reflect upon where it came from. And I don't know, I find it fascinating. And I'm going to stop here and take questions.
Go back to that periodic table.
Sure.
Okay, so some of the like the merging neutron stars, that sounds pretty catastrophic.
Yes,
event.
I did not talk about that at all.
And then, but you have in the same types of elements, you've got dying low mass stars, like orange. Like
Yes.
let's say the second from the bottom line in the periodic table, you've got these merging neutron stars, which are this massive explosion, and then you've got dying low mass stars are also contributing those kind of elements. And that just seems to be like the opposite end of the kind of cataclysmic spectrum. That they're the kind of quietly fading off into oblivion, and yet they're creating some of these more exotic elements.
So I did not talk about all of this at all, and I think it's a separate talk. It's also because it's quite far from my expertise, but yeah, I know that it's not a very satisfying answer to you. But I can suggest speakers who can speak to that. Basically, we have colleagues from the particle accelerator who does all of this, yeah, basically synthesis of heavier elements.
Okay.
Yeah, it is very, very far from my expertise. Yes. Yes.
Yeah.
I mean, a lot of you have seen some of these things, like the Ring Nebula. If you just come here and you knew and you haven't seen it yet, come up to the observatory, we will show you these plans. Now this gives us a greater understanding of what you're looking at. And the Orion Nebula is up there at this time of year, going to be setting next month gradually, but if you haven't seen it come up, we're going to show that to you. You can see it for yourself how that nursery works. Is there, this is a little bit off topic, but we're all patiently waiting for the Blaze star to go off in Corona Borealis. Is there any new thoughts about what's going on there?
I do not know about that.
No,
No,
it's going-
unfortunately, no. But what I can say is that I did not mention this, but astronomers basically have we have different monitoring programs to monitor big parts of the night sky in order to anticipate what we call transient events, right? So waiting for things to explode. So rather than seeing things explode and then going after them with telescopes, we basically are now at the point where we are designing survey telescopes to keep monitoring the sky so that we can catch things before they explode, because it turns out that it is quite important for us to understand where they come from. This is interesting. So I think, well, so I don't actually study stars, I study galaxies. I think there is actually, it's not so simple to get observations into the core, just like we can't really see into the core of the sun very easily, right? But I suppose there could be evidence of that, maybe not directly of, like, I don't think of it as like drilling into the earth and then seeing different sedimentary layers. But I suppose the only way we could study stars is really by spectroscopy. So looking at the light and then trying to identify the different elements and the abundance of the different elements at different stages. And then, yeah, you can work that out by physics. But I think the way we model stars is quite simple, because really, a good approximation would be that, well, stars are stable structure where you have this inward gravitational force. So that helps us to already, just that assumption is allowing us to model like the temperature gradient and the pressure gradient of stars. And it is through this that these calculations that we can understand where are the conditions for the different kinds of fusion to occur. So yeah, I would say that we don't actually have evidence like I can show you, but yeah, that comes from our understanding of physics. It goes quickly by astronomical standards, so it's only like 100,000 years or something. Yeah.
The bigger it is, the faster it burns.
Right.